Hello and welcome back to our channel. For today's video tutorial, let's discuss about computer science, about this chapter 3 about logic gates. So our objective is to prove this particular exclusive OR on how the logic circuit are being constructed from this. How this is possible that it will only work when one of the input is on, while it will not work when the two inputs are on, as well as if it's not on or nothing is working here. So this is what they have mentioned how to write this. And A and not B, or not A and B will give you this result. So our objective now is to prove it using the truth table, as well as with the help of the program I just showed you in the last video tutorial about this circuitry here. But let's do it first manually, and later we can just simply go on with the program to see how it really functions. So bear with me. So this is the activity we have to do. We have to prove that these two statements are actually represented or can be represented by this particular truth table. So that represents and excuse me, the plus represented by the OR, and the dash represents the not. So there is a and B, not B, plus not A plus B. So let's do it first. Okay, let's reconstruct the statement here. So let's reconstruct that one with the statement of would say A is equal to 1 and B is equal to 0. In the middle of it is an OR, while A should be set to 1 and B should be set to 1 here. Sorry, A should be set to 0 and B should be set to 1. It's just like the opposite. So now let's do it manually first, and then in this side we will try to create our truth table. So it's labeled already. Let's just make use of those letters above so that it will not be confusing for us later. So we have two inputs. We have an A and B. So let's just do it here. A, B input. So let's make it a little bit farther from each other. There you go. So it says the between the A and B should be the AND. So the A or the AND gate can be constructed this way. A is 1, so directly connect the A to that particular circuitry. Let's make it a little bit halfway for it. So like this one here, it connects directly to this. Oh god, my drawing. Alright, A connected to this particular thing. Now it says the B should be set into 0. It's not a gate. So what you will do before you hit this particular AND, you should have drawing here of your NOT gate. Connect the B to the NOT gate and then connect this one to that AND gate. So that is what you will have. That is the first statement they have mentioned. Now let's move to the next one. It says the next one here, it says A should be set to 0 while B should be set to 1. So it's the opposite of this thing. So let's just change the color for it. You can take the circuitry from here. This is already that one, and so let's just take it from here, connect to this one here, meaning they are not connected. So let's make it the not A. So this should be not A like this, while the B is set to 1. So now you can take this circuitry or wire and it will just go on to connect to the AND. So it should be like this. Now you have two AND already connected, while these two AND will be connected to the OR. If you observe right now the drawing, it says to the OR gate. Alright, so it should be like this one here. So this is the OR gate we have. Just don't mind my drawing. Alright, anyway, that's the thing. So let's label them all right now. So let's label this one as your C. This is your D, E, F. Alright, so we have A, B, C, D, E, F, and of course the resulting will be, let's take this one as your G at this time. Alright, now let's try to label them based on that. So now what would be the input you can have here? So basically, you will have two inputs, only either zeros and one. So now an easy way to, so that you will not get confused with the numbering of your truth table. This is your truth table here. An easy way for that is to know the binary sequence. So if you know the binary, it's gonna be all start with zeros. So the binary of 1 will be represented by 0, 1. The binary of 2 is represented by 1, 0. The binary of 3 is represented by 2 plus 1. So in other words, this is the whole thing we can have on this sequence. So the first one is the C. The C says not B. So not B means the opposite of B. So this is the B, so it will become 1, 0, 1, 0, because this is the not B here. The D is not A. So this is the thing. The D is not A. So the 0, 0 means become 1, 1, 0, 0. So that's the thing we have there. Now, let's move to the next sequence. So let's just change the color for now so that it will be more visually possible to see. Now, the letter E is the AND between C and A. C and A. So these two here. So the AND. Remember the AND. 2 must be turned on. If you have, if you remember the AND condition should be, both should be 1 so that it will give a result of 1. So 2 input must be 1 so that it will give you a 1. So how we can do that in here? So now you have to look at the A and C, because the A and C is the one that connects to the E. See? It's this one here. This is 0 and 1 should be give 0. 0 and 0 should give us 0. 1 and 1 will give us 1. While 1 and 0 will give us 0. So that's the only thing result for that one. Well, the F, let's change the color again to another color. Let's make it the green this time. So the F is represented. Now, how to get the circuitry that's needed? So look at where it is connected. The first letter that can hit, it's the B and the letter D. So it's the B and the D. So this one here. And again, this is an AND gate. So the AND gate will give you the same thing. So this is 0, 1, so it should be 0. 1 and 1 should give us 1. 0 and 0 will give us 0. 1 and 0 and will give us 0. So that's it. Now, the last thing it says about the OR. Okay, the OR gate, as you remember, the OR gate represented by 1 should be like this. Okay, any of these things will give us a result of 1. So input 1, 0, input 2, 1, it will give 1. Input 1, 1, it will input to 0, it will still give you 1. Input 1 is 1, input 2 is 1, it will still give you 1. Only if it's 0, 0, it will give you 0. Now, let's take a look at this thing here. Now, in this one here, it says 0, 0, so it should be 0. 1, 0 should be 1. 1, 0 should be 1. 0, 0 should be 1. Okay, now, this is the reason why only when it is 1 and 0 will give us this particular 1, 1. Not the 1, 1 will give you this one. So this is the constructions manually of that particular data that we have. This one here to prove this particular first statement. So let's get rid of that and let's try to recreate this one, this particular statement into the this one here in this logic circuit. So let's just flip to the question so that you can remember it one at a time. So it says A and not B. Okay, you have two inputs here. This is your A represented, this is your B representation here. So it says A and not B. So put AND here for your A. Let's do it this way a little bit and more organized. A. And it says not B. So again, because this is not B here, this is not B, so you will put a not in the middle of that, like this one here. Alright, connect this one. This is your not B. Connect that here, and this one should be connected to this one here. So now you have A and not B. The second one, the second area is not A, but it's B. So what you will do with that, you will now get another circuit of an AND. You will put either here or it doesn't matter where. So let's just put it here though. in this area here. So it says not A. So not A. So you will put the logic circuit of a not here. Connect the not for A, and on the first input we have, while B is set into 1. So you can take it from here and connect to that. So now you have two AND, just like our drawing, but this is more organized, of course. And then what we'll do now is in the middle of that there is an OR. So you will now put the OR in the middle of this, and of course connect the two circuitry we have here and put the light bulb on. Connect it. Now expectation, when you click one of it, it will turn on. Click this one, good, it works. Click this one, it works. Click them both, nothing happens. Turn both, nothing happens. So that's it. That's how to prove the first statement, that this particular statement can be used, or this excuse me, this particular combination of circuitry can be used to explain the purpose of exclusive OR. Now the second statement, meaning you not only this one is true, you can also make use of this to make it true. So it says here A or B and not A, or the NAND of A and B. This is the NAND, okay? NAND means not A and B because the line represents not. So since both are having the line above, so means this is not AND. So A or B and this particular thing called A, not A and B. So let's try it again to prove in this area, in this particular situations. Let's rewrite the statement again and see if that will really works. So let's go back to the question just to remember it. It's A or B and NAND of A and B. Alright, or NAND AB. So let's go here. So the statement will become, alright, let's draw it. Alright, A is 1 or B is 1. That's the first one. And it says A is 0 and I think and, yeah, it's and, yeah, because none. Okay, A and B is equal to 0 as well. So this is the statement. So let's try to draw it with the two statement given here. So you should have it an A and B. So since this is an OR for A and B, so you should draw this a little curve thing like this one here. This is the OR. So this is just 1. So connect them directly. That will do. That's the first situation. So you have, and then the next one, both should be 0. So this is the NAND. So if you observe the NAND drawing, it's like this with a circle into it. So connect. Let's change the color again. Let's change the color for this, and let's change the color for this one here. So this is the thing. And after that particular connections, it says that there is an AND. So of course you have to put an AND here like that to connect the OR and to connect this one, and then you can have your result there. Okay, let's try to do the truth table for that using this particular label. So let's assume this is your AB, this is your C, this is your D, and this is your E or X. We will look into it because X is already there. Okay, let's make it an E. Doesn't matter though. So again, the circuitry we have, it's outward 0 0 0 1 1 0 and 1 1. So it's an OR. So just to remind you, the OR is any of the input is 1, it should give you 1. So it's good. The C right now is the OR of A and B. So meaning this is 0, this is 1 1 1. So 1 for all. Now the D, it's the NAND gate. So remember the NAND gate. The NAND gate will give you like this. Both must be the opposite of AND. So if this is your inputs, the only time that it will become 0 is when both of them are on. So all of it will turn on except when it is both both input are on. So in other words, this will become 0, this will become 1, this will become 1, and this is 0. 1, sorry. The last one is another 0. So again, this one here. So 0, both are 1, 0, 1, 1, and 0. It gives you all these things here. Now, our E is an AND of C and D. So you have to look at these two here. C and D should be AND. And remember the AND, both must be 1 so that it will give us 1. So 0, 1, 0, 1, 1, 1, 1, 1, 1, 1, 0, 0. So that's why this is the same result we've got in there. So let's prove it with the logic circuit program that we have. Let's go back to that particular program. Let's just get rid of the drawing above. Okay, let's not get rid of this. Let's leave it there, and let's just construct another circuitry in this side. The same concept. You will have two inputs. While the first one is about the OR of the two, so you just have to put here the OR between these two things here. Connect the OR for that. And another one, it's the NAND. So put the NAND here of A and B. So this is the OR, the first construction, the NOR, in the NAND. If you look at here, so this is the OR, this is the NAND, and this is the that is the AND. So you'll go back there. Alright, so you will put AND after that, then connect them all again, and of course to see the result itself, put the bulb into it and connect. Now both are off, nothing happens. If you click one of it, the circuitry was completed, it's working. If you click the other side, the circuitry is completed. If you turn on both sides, it turns off. So this is exactly. So in other words, let's turn off both of it. Let's switch each of this thing. It works. Turn off both again and turn the other around. It gives the same result. Turn on both, turn off, turn on both. It turns off the light. Alright, I hope you have learned something for today on how we can construct a truth table regarding the situations, and how we're able to prove this particular activity 3.1 into the concept that they represents the same circuitry of the XOR, or the exclusive OR. Thank you for today, and I hope to see you again in the next video tutorial on this channel. Bye bye.